And here are my final comments. We spoke a lot about the difference between relative atomic mass and atomic mass. Relative atomic mass is a dimensionless number, and numbers are not physical quantities, whereas atomic mass represents the physical quantity, mass of an atom, the amount of matter present in that atom. And it is expressed in either the atomic unit U, that is unified atomic mass unit, or in grams or kilograms. If relative atomic mass is not a physical quantity, why are we talking about it? That is because in stoichiometry, that is what I need. Take this reaction in which carbon burns in oxygen to form carbon dioxide. To figure out the masses of carbon and oxygen that completely react with one another, I don't need its atomic mass in some units. All I need is this number. Start with the atomic weight of carbon and molecular weight of oxygen, then add any units you want. To figure out the masses of carbon and oxygen that completely react with one another. So when I am doing stoichiometry, I am not thinking of the physical quantity called atomic mass. I am thinking of the number of times that atom is heavier than another atom, some reference. Let us see if we can answer this question. It says the relative atomic masses or atomic weights of two elements A and B are in the ratio of 3 to 4. Find the mass of B that completely combines with 6 grams of A in the following reaction. And we are given the equation for that reaction. Now, can we even answer this question? Why would I say so? Because we don't know the atomic masses of these elements. Even worse, we don't know the relative atomic masses of these elements. We are given only the ratio between their relative atomic masses. Let us see. We know how to read this equation. First, make sure that the equation is balanced. It is balanced. It says one atom of A combines with one molecule of B. From this equation, we understand that a molecule of B has two atoms. So for my calculation, I can replace one molecule of B with two atoms of B. So one atom of A combines with two atoms of B. Or one gram atom of A combines with 2 gram atoms of B. Now we have replaced gram atom with mole. So 1 mole of atoms of A combines with 2 moles of atoms of B. Now what is 1 gram atom of A or 1 mole of atoms of A? Its atomic weight in grams. Same with B. So what is the ratio of the masses of 1 mole of atoms of A and 1 mole of atoms of B? This. These units get cancelled. So it will be equal to the ratio of their relative atomic masses, where AR A is the relative atomic mass of A, AR B is the relative atomic mass of B. And this is given as 3 to 4. So the ratio of the masses of 1 mole of atoms of A and 1 mole of atoms of B is 3 to 4. Now here we have 1 mole of atoms of A and 2 mole of atoms of B. So you multiply this with 2. So here also you have to multiply 4 with 2. So the ratio becomes 3 to 8. So the ratio between the masses of 1 mole of atoms of A and 2 mole of atoms of B is 3 to 8. That means if you take 3 grams of A, then it combines with 8 grams of B. How many grams did we take? 6 grams. So if you take 6 grams of A, then it combines with 16 grams of B. The ratio must be 3 to 8. So the answer to this question is 16 grams. So we are able to answer this question, though we do not know their atomic masses in any units and their relative atomic masses either. Just using this ratio and this equation, we are able to answer this. And this is what mole concept is about. It is not about the masses of atoms in some units. It's about relative atomic masses or the ratios between relative atomic masses and the relative number of particles that are reacting with one another. This does not mean we don't need the masses of atoms or subatomic particles at all. We need them in atomic physics, nuclear chemistry, and so on. Then how do we measure masses of atoms? Using mass spectrometer. Mass spectrometers are amazing at comparing the mass of an atom with the mass of another atom. We took 1/12 of the mass of a C12 atom as the reference. So we can use mass spectrometers to compare the mass of an atom with this reference to measure its mass in the atomic unit, unified atomic mass unit. Look at this number. The number of significant digits must tell us the kind of accuracy we are talking about. Mass spectrometers are amazing at measuring the masses of atoms in this unit. And if you know the mass of an atom, go use it. There is a small problem here. This U is a non-SI unit of mass. The SI unit of mass is kilogram. So I cannot use the value of mass in this unit in calculations that involves other physical quantities. We can understand this better with an example. Take this famous equation E is equal to mc squared. There are some reactions known as nuclear reactions where some mass gets converted into energy. These are not chemical reactions. And if you want to figure out the amount of energy released, we use this equation given by Albert Einstein. Here, m is the amount of mass destroyed, c is the speed of light in meters per second, then you would get energy released in SI units. Here we cannot use the value of mass in U. We need the value of mass in the SI unit kilogram. So it is for this reason we need to know the masses of atoms, subatomic particles in kilograms. But how do we figure out the masses of atoms in kilograms? Mass spectrometers are good at measuring masses of atoms in U. Let us see. How can we figure out the mass of a single grain of rice accurately in kilograms? I can think of two options. The first option is to take a single rice grain and weigh it using some kind of balance as accurately as we can. The second option is to take a large collection of rice grains, if they are all identical, and measure the mass of that collection using a balance as accurately as we can. Also count the total number of rice grains in that collection as accurately as you can. Then divide the mass of the collection of grains with the number of grains in the collection. That will give you the mass of a single rice grain. So we can determine the mass of a rice grain using both the options and take whichever we think is more accurate. Same with atoms. We have two options. We have two options here. The first option is to directly determine the mass of an atom in kilograms. How can that be done? With the help of the same mass spectrometer. In a penning trap mass spectrometer, we measure the rotational frequency of the ion. The rotational frequency of the ion, charge on the ion, mass of the ion, and the strength of the magnetic field are related by this equation, and you don't have to memorize any of this. Just follow the argument. To get an expression for the mass of the ion, move m to the left hand side, f to the right hand side, then m is equal to q times b over 2 pi f. Now we may argue that if we substitute the values of f, b and q in SI units, then we would automatically get the mass of the ion also in SI units, that is in kilograms. Of course we can do that. We can measure this rotational frequency with great accuracy. We know an accurate value of the amount of charge on the ion. So if we can measure the strength of the magnetic field also to a high degree of accuracy, then go for it. Then the mass of the atom determined in kilograms would also be very accurate. But the problem is we cannot measure the strength of this magnetic field with great accuracy. Therefore, the mass of the atom determined using this method in kilograms will not be as accurate as we like it to be. But let us not discard this option just yet. Let us look at the second option also. Then we can compare both the options to decide which is better. Before we discuss the second option, let us try to understand what a mass spectrometer is very briefly. The very first generation mass spectrometer is simply a discharge tube with some extension. You remember the discharge tube used by Goldstein, in which he discovered canal rays with the help of a perforated cathode? We have the same arrangement here, but we made a small opening here, connected it to a long tube and applied a strong magnetic field at the other end of the tube. Also, we placed a photographic plate here. This is a photographic plate. When a high voltage is applied between these two plates, some positive ions are created here and they pass through the holes of this cathode. They enter this tube and exit at the other end. When a moving charge enters a magnetic field, it gets deflected continuously. So it describes a semicircular path and finally hits the photographic plate at a particular point, making a dark line there. And this is the diameter of that semicircle, so half of it is its radius. So we can measure the radius of this semicircle. Now imagine two ions with different masses are passing through this magnetic field simultaneously. Let us assume they are carrying the same amount of charge. Then what happens? Both the ions get deflected, but it is easier to deflect a lighter ion than a heavier ion. Remember inertia. Therefore, the lighter ion gets deflected more and it makes a smaller semicircle, and the heavier ion gets deflected less, so it makes a larger semicircle. But we can measure both the radii with the help of this photographic plate. By using laws of mechanics and electricity, we can derive a relationship between the mass of this particle and the radius of the semicircle it makes. M directly proportional to R square, or M1 over M2 is equal to R1 squared over R2 squared if all other parameters are same between the ions. That is, they are carrying the same amount of charge, passing through the same magnetic field, etc. So we have a relationship between the ratio of their masses and the squares of the radii of the semicircles they make in a magnetic field. By definition, atomic weight is mass of an atom over 1/12 of mass of a C12 atom. Now, if M1 is the mass of this atom, M2 is the mass of this reference atom C12, then M1 over M2 is equal to R1 squared over R2 squared. So we can replace this with R1 squared over R2 squared. So atomic weight or relative atomic mass will be equal to R1 squared over 1/12 of R2 squared. And we can measure R1 and R2 in the mass spectrometer. So we know the value of this term on the right hand side. So we know the atomic weight or relative atomic mass of an element. Interesting thing here is we are determining atomic weights using mass spectrometer not by measuring their masses in kilograms or some other units, but by measuring the radii of the semicircles their ions make in a magnetic field. See, we are measuring R1 and R2 and using this relationship between the radii and masses, we are able to determine the atomic weights. So don't think that in a mass spectrometer we measure the value of M1 in kilograms, M2 in kilograms and divide one with the other. We don't do that at all. We are measuring something completely different. We are measuring the radii of the semicircles. Today we have far more advanced mass spectrometers and we have different types of mass spectrometers. We use a particular type of mass spectrometer known as Penning trap mass spectrometer to determine relative atomic masses or atomic weights. In this mass spectrometer, we do not measure the radii of the semicircles. We instead make the ion rotate and measure the rotational frequency of the ion. Obviously, if the mass of the ion is more, its rotational frequency will be less. So they are inversely related. So M1 over M2 will be equal to F2 over F1. So the expression for relative atomic mass or atomic weight will be F2 over 1/12 of F1. And we can measure F1 and F2 with tremendous accuracy, with phenomenal accuracy. So we can determine atomic weights with great accuracy using modern mass spectrometers. Even here, we determine atomic weights by measuring the rotational frequencies of the ions, not their masses in kilograms separately and divide one with the other. I know this is a very oversimplified description of these mass spectrometers, but the point I am trying to highlight here is we determine atomic weights not by measuring their masses separately in kilograms, but by measuring some other property like the frequency of the ion or the radius described by that ion in a magnetic field. Now the second option, using the same Penning trap mass spectrometer, we can determine the ratio between the mass of an atom and the mass of a C12 atom with tremendous accuracy. How? You just told us that we cannot accurately determine the mass of any atom with great accuracy because we cannot measure the strength of the magnetic field to a high degree of accuracy. So you cannot determine the value of M1 in kilograms accurately. You cannot determine the value of M2 in kilograms with great accuracy. But you are saying you can determine the ratio accurately? Yes, that is the beauty of it. See, if both the ions are passing through the same magnetic field, maybe simultaneously, then B is same in both the cases. So, if I take the ratio between these two, the B's get cancelled. Assuming they carry the same charge, Q's get cancelled, these numbers get cancelled, so I am left with F2 over F1. And I can measure F2 and F1 with tremendous accuracy. Therefore, I can measure or determine this ratio very accurately. So, I am not saying that I will determine the value of M1 in kilograms and M2 in kilograms separately using the strength of the magnetic field and then divide one with the other. Then it will not be accurate. But I am passing both the ions through the same magnetic field, maybe simultaneously, so that I don't even have to measure the strength of the magnetic field. If I take the ratio between these two, then B's get cancelled. But whatever is left in the equation can be measured with tremendous accuracy. That is why mass spectrometers are very good at measuring the mass of an atom relative to the mass of another atom, as we discussed before. So, if you take a sodium atom, you will find its relative atomic mass is this, a very accurate value. So that means we have a very accurate value for the mass of an atom in unified atomic mass units. Fantastic. We are very happy about it. But that is not what we are looking for. We are looking for the mass of an atom in kilograms. And we tried to determine the mass of an atom in kilograms, and we did a decent job there. Remember? But let us see if there is another option to determine it even more accurately. See, by definition, the relative atomic mass of C12 is 12. That is what we did in 1961. And the molar mass of C12 isotope will be its relative mass in grams per mole. Then the mass of 1 mole of C12 would be 1 mole multiplied by its molar mass. So it will be 12 grams. And obviously in 12 grams of carbon 12 isotope, there will be a very large number of carbon atoms, C12 atoms. What if we could experimentally measure the total number of C12 atoms present in 12 grams of carbon very accurately? Great, that would solve our problem. And that is what we did. But because C12 was not workable, we instead measured the number of atoms present in 1 mole of silicon 28. And 1 mole of any substance has the same number of particles, right? We don't have to get into those details, but understand that we experimentally determined very accurately the number of C12 atoms present in 1 mole or 12 grams of C12. And this is that number. This is what we call Avogadro's number. And this is a very accurate measurement. So that means these many atoms of C12 isotope weigh 12 grams. Then what will be the mass of one C12 atom? Mass of one C12 atom will be 12 grams over Avogadro's number. But one unified atomic mass unit is 1/12 of the mass of a C12 atom. So 112 times 12 grams over N0. So it will be 1 gram over N0. Substitute the value of N0 and simplify it. You will get the value of one unified atomic mass unit in grams. And this is a very accurate value because we determined the value of Avogadro's number with great accuracy. Once you know the value of 1U in grams, you know how to calculate the mass of any atom or subatomic particle in grams or kilograms. Take the relative atomic mass determined using the mass spectrometer, multiply it with the value of 1U to get the mass of the atom in grams. See, we obtain a very accurate value for the relative atomic mass from the mass spectrometer. We obtained a very accurate value for 1U in grams because this Avogadro's number is very accurate. That means we are multiplying two very accurate values. Therefore, the mass you calculate in grams would also be very accurate. Now, you compare these two options. What do you think is a better option? I think this is a better option than the first option. That is why we don't use mass spectrometers to determine masses of particles in kilograms. We calculate the masses of particles in kilograms using this method. We use mass spectrometers to measure masses of particles in unified atomic mass unit, not only because those numbers are convenient to us, but also because we can measure them with terrific accuracy that is required to calculate masses of such small particles in grams and kilograms. In 1808, John Dalton started determining atomic weights using mass of a hydrogen atom as reference and chemical reactions, and his atomic weights were terrible. About 100 years later, we switched to oxygen reference, and physicists and chemists ended up on two slightly different scales. They used two different AMUs. In 1961, we unified these two scales using carbon-12 atom as the reference. Today, we determine relative atomic masses using advanced mass spectrometers, and the accuracy of these relative atomic masses is phenomenal. Now you may be wondering why we are still using the idea of atomic weight or relative atomic mass that Dalton used more than 200 years ago. Why we are using masses of atoms relative to the mass of another atom taken as reference. You know, our present reference for atomic weight is 1/12 of the mass of a C12 atom. The reason is atomic weights or masses of atoms relative to the mass of another atom are convenient to us. Look at these numbers. These numbers are convenient to us. Whereas these numbers are not. These are masses of atoms in kilograms. Secondly, even to determine the mass of an atom very accurately in kilograms, we need their relative atomic masses or atomic weights, because mass spectrometers determine relative atomic masses more accurately. That is, masses of atoms relative to the mass of another atom more accurately than in kilograms. That is why we are using the idea of atomic weights or relative atomic masses even today. And for academic purposes, we can take the value of Avogadro's constant as 6.022 into 10 to the power of 23 per mole, and the value of one unified atomic mass unit or 1 Dalton as 1.66 into 10 to the power of minus 24 grams or 1.66 into 10 to the power of minus 27 kilograms. And that is the story of mole concept I wanted to tell. I hope you find it useful, and thanks for watching.